that was just an idiosyncratic notation. It was just trying to emphasize that when it makes a difference, the covariant derivative should be taken. But what this really means, if you want to not introduce a special notation like this, and this is confusing and did confuse some people because it looks like it's talking about taking the covariant derivative of x, which of course wouldn't make any sense. X is not even a vector. It's just a point in the manifold. So there's no such thing as the covariant derivative of it, except in a trivial sense that it's just the tangent vector, which is in fact what I meant. So if we define u temporarily to be the tangent vector to the curve, okay, so that means if we write it out in full, it means I forget the different notations that we're using, but it means gamma dot of lambda. In other words, the vector that the vector as equivalence class of curves that gamma belongs to. That is the i.e. UA equals equivalence class of curves. I'm using the particular definition of tangent vector that we used here, to which gamma belongs. So, and of course, that means the one to which it belongs at the particular value of lambda. So in other words, this is an element of the tangent space to the manifold at the point gamma of lambda. Okay, so those are just... So the important thing is that it's, or another way of saying it is that what I said in words, I can write it also. UA is the tangent to gamma parameterized by lambda at gamma of lambda. When I say tangent, of course, I mean I'm treating gamma as a parameterized curve. In other words, a map of the real numbers or some portion of the real numbers into the manifold. Just recalling all our definitions. So we take the rate of change of x along lambda, so to speak. That's what we meant. That's what we mean by the tangent vector, right? It's the infinitesimal displacement dx normalized by the change in lambda. Okay, so that's all notation. With that notation, then by this I really meant d by d lambda of u of a equals 0. In other words, the tangent vector to the curve is parallel transported along the curve. It's parallel transported because the right-hand side is 0. So its rate of change as measured by parallel transport is 0. And then remember that we said we had another way of writing this, which was dx d lambda b grad b u of a equals 0. This is yet another way to write. I mean, all these three things. This one, which is just a notation. This one and this one are equal. And at the time we noticed, this looks like it's slightly different because it seems to involve the covariant derivative of u in all directions in order to get the gradient. But in fact, it only involves knowing the restriction of u to the curve along which you're taking the derivative, as we saw. And of course, because this derivative we've defined to be u, I can also write it, therefore, in a fourth way, ub grad b ua equals 0. So that's another way of writing. I suppose the two sort of most important ways to write it that would be completely correct, so not using a new definition here, would be these two. Either one of these, which are equivalent, are the geodesic equation. Okay? So, okay, hopefully that clears it up if there was any confusion. Any other questions? Okay, so if you remember from last time, we had written down an action principle, which was that for an arbitrary space-like or time-like or null geodesic, the last two being the important cases, we had written an action for a particle of mass m, which was 1/2 integral dx dot dx minus m squared d lambda, and traced out its consequences, derived the geodesic equation from it, and so on. And it also derives from it the conservation laws that go with the existence of any killing vector. But there is a kind of question that you could raise here. What's the physical meaning of this lambda? So I wanted to make just a few comments. I mean, this thing, or I could even maybe put the metric in explicitly. All this is clear. We're talking about some curve, gamma, which is basically just a subset of the space-time, a one-dimensional subset of the space-time. But here we've chosen to parameterize it in a particular way by this parameter lambda. And furthermore, that parameter is actually entered into the action. So it's unlike the other action that we had for the massive case, where we had, minus integral of m d tau. That's just marking off the total length along the curve, proper time in this case, and using that as the action. So it has a direct physical meaning, if you think in terms of clocks, for example. And it involves nothing more than the curve itself. If you were to introduce the lambda would drop out because it's under a square root, if you remember. So, this rate of change squared is under a square root. Anyway, in such a way that the lambda isn't there. Yet here the lambda is there. So what does it mean? So I think one comment is that it might be better to think. So this is just a bunch of comments. It doesn't add anything to the formal developments that we've done, but maybe it adds something to the physical interpretation. So we might, instead of writing d lambda, we might want to write, I don't know if you can ever write this well. I don't know if you ever saw this notation, like maybe it's taking thermodynamics or something like that, and people talked about dq, and then maybe if you never see that notation, it won't really help to clarify. But like in thermodynamics, you might have things like dq is equal to TdS or something like that, if you remember such a formula. But then people point out that this is not really a differential in the same sense. It's not really the change of some quantity q. It just represents an amount of heat transferred. Whereas this is really the change. This S, of course, is now the entropy, which is going to be in a few minutes also here. It's unfortunate that the entropy and the action functional are represented by the same symbol, and you need to use both, which we will. But in any case, this is really the change of something. It's the change of the entropy of the system under consideration. But this is not the change of the heat content of the system under consideration. There's no such thing as the heat content of a system. But there is such a thing as a heat transfer. So sometimes, I guess no one ever saw this notation, but somewhere I've seen. You saw? Yeah. Does anyone else see this notation? A couple of you. Oh, and so it's not so uncommon notation. So represent that it's just a change of something. It's just an amount, an increment of something. Or that makes it sound, it's a very small amount of something, but it's not the change. That amount doesn't represent actually the change of anything that has an independent meaning. And so this lambda is to a certain extent like that. It's really the d lambda that counts. It's not that there's necessarily some lambda it's not, for example, that lambda equals 5 here would be a different world than if lambda equals 6 or something like that. The only thing that counts is this d lambda. So one way of saying that is that we could think of it as what's called a one-form or a covector on gamma itself. So remember our picture of a one-form covector was like this, parallel planes in the tangent space. So this is just a one-dimensional object, so the picture of the covector would be exactly what I've drawn here, so little ticks like this. And it's showing you basically what d lambda is between one point and another. So it's maybe better to think of it as a covector, but still that doesn't explain, I think it is better to think of it as a covector. If you do that, it also makes it clear why you didn't want to hold lambda fixed at the endpoints when you did the variation, because what you're really varying is this covector field along the world line. But it still doesn't explain what the physical meaning of that. So we saw something very similar to that when we were doing the Friedmanian cosmology, and then we had in fact exactly something like this, d tau, which was the analog of d lambda here. It was multiplying some other stuff. In fact, it is the same thing, actually. One of the things that it multiplied was the total mass. But it also occurred in other ways, something like this, quite analogous to this. But in that time, in that case, we understood what it represented. It represented elapsed time between different hypersurfaces of the universe. In this case, it's just something that we've introduced. But I think, so we might ask, what does it represent? So here's I suggested before that you could get this out of geometrical optics, and to a certain extent you certainly can, but whether you can derive exactly this action off shell, which, of course, when you're not dealing with solutions of the equations of motion, I'm not sure exactly whether that's possible. But in any case, it has something to, if that's right, it has something to do with wavelengths, and quantum mechanically, that seems sort of reasonable. So let's think about that for a little. First, notice that the relationship between P, remember, P was dx d lambda, or if we like, dx is P d lambda, where dx is a little increment, infinitesimal displacement along the curve. So this is momentum, and we know, if we think quantum mechanically, this has something to do with wavelength, because d lambda basically is a ratio of two vectors, both tangent to the curve, one the displacement vector and one the momentum vector, if you believe that the momentum is parallel, is itself tangent to the curve, which is something you can get from special relativity. In the case of light, it's also true, and again, you can sort of deduce that by thinking about wave packets. So that thing suggests that this lambda carries information about wavelength. If we think about the dimensions of lambda, we can get a little deeper insight into it. So by this I mean the dimensions that it carries. If the dimensions, so what is it? It's a ratio of a length to a momentum. But a momentum, of course, is a mass times a velocity, or in the time-like direction, it's an energy. But both of those, since once you set the speed of light to 1, velocity is dimensionless. And so both momentum and energy have the same dimensions, which is the dimension of mass, right? And now, if we also set h bar equal to 1, which normally you shouldn't be worrying about in the case of classical gravity, but if we're now thinking of an individual quantum like a photon, then let's say we also set h bar equal to 1, then this just looks like a length squared, right? Because the mass is 1. In units of h bar equal 1, mass and length are inverses of each other. So in some sense, this d lambda is an area or an infinitesimal area. What could that mean? So let me just address, in the case of positive mass, you don't seem to get anything particularly illuminating. You can see that lambda represents basically the proper time elapsed times the period of the wave, whatever that means. I'm not sure, but I guess, yeah, I have to think. I can't at the moment think of a nice geometrical picture for that. But in the massless case, there's an interesting picture. So let's take the case where mass equals 0. And now I'm drawing a picture of a plane wave, or of a wave packet, let's say. How does a picture of a plane wave look? All my pictures look basically the same. So here's another one. So a plane wave looks something like this. What am I drawing here? I'm drawing the surfaces of this is a space-time diagram. I'm drawing the surfaces of constant phase. So this would be like the trough of the wave. This would be like phase equals 0. Let's call it the trough. And then this would be the crest of the wave. This would be the trough, crest, whatever. Just pick out some constant phase and draw the surfaces. So you see what this is. This is a two-dimensional drawing, but if I could make it three-dimensional, it would be just a series of parallel planes, which is also a one form. But it's important that these would be light-like planes. In other words, the tangent vector, well, now it's sort of obscured a little bit what's going on here, but if we forget, just think of the cross-section, which direction is the wave going, if you ask yourself? Well, if you think about it, these are points of constant phase. So if you just track how a point of constant phase moves, that's the direction that the wave itself moves, right? And so the wave itself is going like this, in this direction. So k, or p, which is h bar k, where k is the wave number, the four-dimensional wave number, is pointing along itself, pointing along these lines. Okay. So here, let's go back to blow up a little portion of it. So this is from one wavelength, one trough to one trough of the wave, for example. Now, if you take a I don't think I'll prove this, but I'll leave it to you. I think I'll leave it to you to prove as an exercise for the reader or the listener. But if we take a plane wave, a light-like plane wave, and if you consider adjacent crests, let's say, or troughs of the wave, and this is a certain amount of the propagation of the whole world line of the photon, then this area, I claim, is proportional with an appropriate normalization, that this area is proportional to d lambda along the curve. It has to do, you have to think about the fact of how this p is related to the wavelength, or how this k is related to the wavelength. So the way in which it's related is that the wave, now I'm writing this as a flat space relationship, so think of it just locally. That's the idea of a wave packet, so everything is approximately flat. So what we're saying is that the wave is the phase of the wave is given by e to the I k dot x, sort of phi of x is proportional to this, e to the I k x. That's the meaning of this wave number, right? So if you put all those things together, you'll be able to convince yourself that in fact that gives at least a geometrical interpretation of lambda. So it means that it does refer to a wavelength, and it can be interpreted geometrically as an area swept out by the region between two space-time area swept out by the region between two corresponding points on adjacent loops of the wave as it goes a certain distance along the curve dx. Dx is this, right, along the direction of propagation. Okay? Yeah?
It was just bothering me which way you drew the momentum, because I thought that if we drew the surfaces of constant phase, the momentum would be perpendicular to that.
It is. It is. But we're in Minkowski space now.
Oh.
So what's the, yeah. So that's a crucial point, right? So a light-like direction a light-like vector is perpendicular to itself. And in fact, not only is it perpendicular to itself, but this plane that I drew here, if we could go up to higher dimension, it would be a 3 surface, right? This plane, it's not only perpendicular to itself, but it's perpendicular to the whole plane. So the normal to this plane is precisely a vector k like this. Okay, so this is the unique direction that's orthogonal to every vector lying in the plane. That's a very important thing, which is completely counterintuitive when you first see it. But that's the way Lorentzian geometry is. There was another question? Yeah.
Now I'm confused as to why the surfaces of constant phase are light-like.
Their world lines, so to speak, are light-like. So imagine a wave packet like this. So by constant phase, I mean pick out, say, the peak of the wave, and it's propagating like this, right? But now I'm drawing a spatial picture now. The whole thing is going at the speed of light, at speed 1 in this direction. So every point on it, so to speak, is going at the same speed. So the trajectory of this point in space-time, if we had its true plane wave in flat space, would be exactly a null vector, a light-like vector. Because it's a motion of some point that goes at the speed of light.
Oh, so you mean to say that in your diagram, one of the directions is time?
Oh, this is a yeah, I did say, but that's right. This is a space-time diagram.
Yeah,
This here is a space-time diagram. Otherwise, it certainly wouldn't be the case that this was normal to itself. So, in space, of course, it would look the other way, like you suggested. You'd have something like this in the direction of propagation. It would be like that. But what that is some sort of, what is that? It's some sort of projection down of this vector on pure space. It's a little hard to draw. I guess it's a little hard to see. But if you sort of slice this this picture, which is already getting hard to decipher, if you sliced it at a moment of time, then you just have a sequence of, if you imagine it in 3 dimensions, of lines coming out like this. And those would be those surfaces of constant phase, and then perpendicular to them would be in this direction. So that's the projection of this space-time momentum vector or wave number vector down onto space. That's the picture that you usually see. Okay, so anyway, this gives, I don't want to dwell on it too much because I don't know whether or not it has a deep significance, but it's actually very useful to be aware of this relation to area. It helps you in thinking about and understanding I claim, although don't press me on this right now, it helps you in understanding things like the instability of the Reissner-Nordström extended space-time, where you have an instability where a whole bunch of wavelengths all bunch up. And because of that, you can see that there will be a blue shift associated with it. And that blue shift is thought to actually destroy the space-time, create an instability so that you, for those who know about Reissner-Nordström, so that you can't actually go in and come out into another world. You'll hit some sort of infinite energy density first. Anyway, it's something between a curiosity and a deep fact. I'm not sure where it exactly sits there. So the other thing I wanted to mention, which I already did once, is that now that we have the covariant derivative, we can write down the action for a scalar field. We won't be doing anything with it just now, hardly anything. But if you wanted to think about the meaning of this in terms of geometrical optics, you would want to know what the wave equation is in curved space. And I already wrote last time, for the massless case, it's just this equation, which can be written as grad A, G, A, if you like, grad A phi. Again, this grad A phi doesn't need the covariant derivative again. It's something like an overkill of writing a kind of covariant derivative expression where you don't need one. But it's not false in this case. It's literally true. So this is the box. This is the this is equal to box phi. And I said that last time. The other thing that I didn't say that I just wanted to mention is that, interestingly enough, to write the action from which this comes, you don't even need the covariant derivative. You need it to write the equation of motion that comes from the action. But if you just want to write the action, it comes from, if I got the sign right, grad phi squared, which we could write as grad A phi, GAB, d integrated over the region in question, whatever it may be, that you're computing the action, this being the 4-volume, as usual. So here, of course, I wrote it as if I did have the covariant derivative, but these are just gradients, so I could really just write this as gradient A and gradient A. And then there's no covariant derivative there at all. Okay? This is in the massless case, of course. One interesting observation, which is actually quite important, is that you may have run across or may not, is the so-called conformal invariance of this wave equation. That means that it doesn't even, not only did it, it didn't need the covariant derivative. It had needed the covariant derivative. Remember, the covariant derivative needs the metric in order to be defined. Here, it still needs the metric, but it doesn't need the covariant derivative that comes from it. But the observation is it doesn't even quite need all of the metric. It doesn't. There's a scale that drops out. So if you rescale the metric, you'll easily check in. This is limited now to 4 dimensions. To 2 dimensions, sorry. So if you check this in 2 dimensions, I didn't say it. I forgot to say that when I said it was conformally invariant, I'm talking about 1 plus 1 dimension, 2 dimensions of space-time. And if you look at how these things scale in 2 dimensions, then you'll see that the overall conformal factor, if GAB were to go to some sort of omega squared GAB, then omega squared would drop out of this thing. So in 2D, it's just the conformal metric. That enters into the action. Anyway, once you have it, then you can start doing geometrical optics, and you can verify, in fact, that the suitably defined. If you use this kind of, geometrical optics means that k is a very large number. Basically, I won't go into the detail of what the full approximation is, but basically, it's just saying that k is very large, and if you sort of plug that into the wave equation, you'll be able to see that, in fact, you get the geodesic. And if you plug that into the wave equation and you use the other thing which we used, which was k equals gx d lambda. I'm setting h bar equals 1 here when I say this. Then if you use that together with and if you use that definition, you'll see or even if if you use that definition to determine how the parameter lambda runs, what is d lambda, then you'll see that with that lambda is an affine parameter, and that k follows the geodesic equation. In other words, the rays of the light or of this field are geodesics affinely parameterized by lambda. So it doesn't, as I said, it doesn't quite show you, as far as I can see, what this action means off shell. But anyway, it makes contact with a kind of field theory, which is in fact the one that we have to use to represent light, although light, of course, has polarization also. Okay, so there's a couple of other things that I wanted to derive from the action principle that we had. This one I think is called Fermat's principle, also called maybe principle of least time, or I forget exactly all the different names that it might or might not have. I think it has those two names. But in any case, we'll see what it means. We'll see in a second what it says. It's something that tells you, in the situation where you have a stationary space-time. So remember that what that means. It means there's some killing vector, leak C, such that the killing vector along that direction of the metric is 0. We know we started with this variational principle, this action principle up at the top, that governs the motion in the sense of governing what are the paths through space-time, the world lines that this particle will follow. But if you have a stationary situation, it's also interesting to ask, what about the spatial paths? How can we work out what you might call the orbit, of the object, just in space, without worrying about how it evolves in time? And that's always possible when you have a stationary metric. Yeah.
Sorry, I was just curious about this. For a stationary metric, can we have a killing vector that varies in space, or does it have to be?
Oh, absolutely. So, well, of course, you have to ask.
Well,
I have to ask you what you mean by varies in space. But if you mean this, so what I mean, so here's our killing vector, whatever it's doing. Actually, a nice one to draw would be like this. This is sort of how it looks in the neighborhood of a black hole horizon. But this would be, so you can see that it's certainly varying in the sense that it vanishes right here, and it's different. Its lengths are different, and its direction different from. So if I took this in Minkowski space, and this is called the Rindler killing vector, I think, or anyway, it's the Rindler wedge, as it's called, 1/4 of Minkowski space, and then this is the killing vector that there's actually. I mean, none of this directly relates to your question, but it's a good example to think about. This is called the boost killing vector. It's the infinitesimal boost, the infinitesimal Lorentz transformation along that direction. So if I draw this, now we're actually in flat space in this case, so we can give a direct meaning to your question, which is, does the killing vector vary from point to point? And obviously it does. Here it's pointing vertically in this frame, there it's pointing. So, and as you go out along the light cone, it's asymptoting to the light cone. So it's going from light-like in this direction to light-like in this direction, to time-like to 0 here, and so on. So I think the answer has to be yes. But we also have to ask what your question would mean in the curved space case. In the curved space case, I would say that the question, I would translate to this question, is the covariant, we can't ask what it means for the killing vector to be constant without some qualification, but we can ask what it means to be covariantly constant. That is, if you transport it from one place to another, you get the same thing that's already there. It goes unto itself under parallel transport. That's we would write like this, and then we can see actually the relation between this equation, which is what you're asking, and the killing equation. So remember what this equation looked like. It said grad A CB plus grad B CA. Remember, that was the equation, because the Lie derivative of G is precisely this thing, as we've computed before. So if this vanishes, obviously this vanishes, but this is a much stronger statement. Having a covariantly constant vector field is much stronger than having a killing vector. But in flat space, you know what all the killing vectors are. And so if we go back to flat space, this would just say a constant vector field in the vector space sense of constant, and that would be translation. So it would be either in a particular frame, time-like translations or space-like translation, and there are 4 of them. One corresponds to energy, and the other 3 to components of the momentum, spatial momentum. And then, so there are solutions like this, but there are also solutions like this that don't satisfy that, and that's these, and those are they're actually linear. I mean, this is constant. If you write out the other ones, the boost killing vector, in terms of some coordinates. So now I'm writing a vector space. So this is in Minkowski space now. Then if I write some sort of omega AB xb, x is now a vector because I have, maybe I should write it x minus 0. I choose an origin, and then I'm interested in the value of killing vector at some point x. If I use an equation like that, which you would call a linear dependence on the components of the vector, that'll give you the other killing vectors if you take this to be an arbitrary skew matrix. So there's 6 more killing vectors. And what are those? Well, think about it. What symmetries do you know from Minkowski space? We knew the translation symmetry, right? So what else? There's one obvious one that we know about, which is rotational invariance. That's 3 more, right? This is a 4x4 antisymmetric matrix. If we write out in components, it's an antisymmetric tensor in 4 dimensions, so it has 6 independent components. It's a 6-dimensional space of tensors. And what are the other 3? Those are, of course, if you think, what have we left out? From the Poincare, we've left out the boost, right? So it's the 3 boosts, if you like, the boost in each of the 3 orthogonal directions. So the point is that it can vary, but it has to vary in general, there won't be any killing vectors, and if they are, they're highly constrained. They can't just vary any old way. This is a very restrictive equation. In this case, in flat space, it tells you that this has a linear dependence. If you're interested in conformal killing vectors, then you can get quadratic things. Okay. So, any other questions? So we go back to Fermat's principle. So the picture here is, suppose you're thinking of motion in the neighborhood of the sun, and you want to know plot the orbit. You want to know, you look out in the sky and you plot the locations at different times, but you don't worry about the times. You just want to know what orbit is it following, or the planet following around the sun. You want to know that it's an ellipse, for example. So, or if it's a beam of light, you want to know it's going past the sun and it's bent a little bit. So if you're not interested in the time delay, which is very important, but suppose you're not interested in that, you just want to know how much it's bent, which were the early observations, then all you need to know is this orbit. So we're asking, so it's just an interesting fact that when you have a stationary space-time, that you can write down an action principle that directly governs this orbit without talking about the space-time trajectory. I won't go into, there's actually a general method for it, which I won't go into. So I'll mention something, again, something you might like to work out. there's a general method for doing this, and it follows from the identity, from the following identity. And how do you something identity, which is that this is a kind of interesting thing about action principles. That remember, we defined the action however we defined it. There it is for the case of a massive particle. But it's interesting that it can also be written like this, where this is where the PA is defined as always as dx d lambda, and in this case, but in general, you always have this relationship. So you integrate P. This, of course, is the space-time momentum. But you integrate. So if we were to write it out in a particular frame, then it would look like minus E dt plus P dot dx. It would be that integral. That would be the integrand in that case. But it's interesting. I mean, you recognize this, of course. That's the change. If I put here a delta and not a d, it's the thing that enters into the variation of s when you're at a solution. But this is a general statement for any trajectory. So using that, you can always get an equation just for the trajectory. What's going on is that we have here space-time. We have a curve gamma. We have here just space. And we have the image of that curve, right, just into space. And this space really, I'll call m bar. What it is technically, this is exactly what we did when we talked about reference frames. It's called what you might call the quotient of m with respect to the Killing vector. In other words, if you chose a reference frame whose particles were following the Killing vector, they were in some sense stationary in the sense of the Killing vector, then each of those whole world lines represents a point of space. Okay, so that's kind of the mathematical, and it's in that space, m bar, which I've written here as a quotient, that the orbit is actually defined. So that's kind of the background. And as I said, there is a general method, but in the case of zero mass, it's enough to know that that general method exists and just play around, and you can easily produce the effective action that describes the orbit directly. That's what we'll do here. And the result is what's called Fermat's principle, which tells you that for the particle, or for the photon, let's say, to get from one point in space to another point in space, the actual trajectory that it follows will be the one such that the elapsed time is the least compared to all other trajectories. What we'll actually prove is that it's stationary compared to all other trajectories. Where time means time in this Killing sense, it's the time in which it's the time coordinate, which has the if I think of t as a function on the manifold, the time coordinate, it's the one such that Lie derivative along c of t is equal to 1, which, remember, we can write as ca grad a t equals 1, where I'm treating t here as a coordinate function. In other words, as we saw before, mapping the manifold into the real numbers. It's also, if you think back to when we were discussing all that stuff, it would have been what I would have called x, capital X0, the zeroth coordinate function. Okay. So that's the time that we're talking about. Yeah.
So what a time like Killing vector does for us is basically specify a slicing on which to project.
No, it's the opposite. It doesn't specify. That's the interesting thing. It doesn't specify a slicing. It could, and there are certain circumstances. So this is the crucial distinction between a quotient manifold and a submanifold. So if we were dealing with a slicing, then we'd have a submanifold, just a three-dimensional subspace of space-time. But a quotient is not asking us to do that. What it's doing instead is it's collapsing each world line each orbit of the killing vector, it's collapsing into a single point. So it says they just regard all those as the same point. But it doesn't tell you any particular slicing that comes from that. And in general, there won't be a natural one.
What do we mean by orbit?
By orbit, I mean a path in that quotient manifold. In other words, it's a succession of trajectories of the killing vector. It's a succession of integral curves of the killing. It's just a succession of positions. So it probably looks a little abstract. Let's make it very concrete in the following way. So let's now choose a coordinate system which is adapted to the existence of this symmetry, this killing vector. In other words, let's choose a coordinate system such that the zeroth basis vector is C itself, which is a killing vector. If you remember, and also I'll write, as I've already done, x0 I'll call t. If you remember what this meant when we discussed killing vectors, in this coordinate system, the Lie derivative is just the partial derivative. In other words, if we represent everything in terms of components, then the Lie derivative is nothing more than the partial derivative with respect to time. The components of the Lie derivative of some tensor are just the time partial derivatives of the components of that tensor if we express those components in such a coordinate system. Okay? So now, stationarity, when we say that the metric is stationary, all we're saying in these coordinates is g alpha beta partial t equals 0. In other words, we're saying that the metric is independent of this time, this particular time coordinate. So, so it means if we were to write out ds squared, blah, blah, it'll have in term like g00 dt squared. And all these coefficients, none of them will involve the time explicitly. The only place you'll ever see the time is in this dt squared and in dt dx. I mean, you'll see dt's, but you'll never see an explicit dependence of any of the coefficients on t. So that's what it means. This is, of course, this is exactly, if we hadn't gone through this geometrical discussion and just asked, what do you mean by a stationary or a time-independent metric, this is probably what you would have said anyway. And that's all the killing vector is really doing for us. Okay? So now when I talk about a spatial orbit, I just mean, say, gamma bar, which will map R into, in this case, in this coordinate system, it'll map R into R3, locally anyway. In other words, it'll give us the three coordinates. In other words, gamma bar of lambda will just equal three coordinates, x1 of lambda, x2 of lambda, and x3 of lambda, right? It's just a set of three numbers. And so, but these three numbers, what are these three numbers? They're not, you could of course get them by, I mean, here's the killing vector. I'm trying to draw this, which I can't really, I'm trying to draw it as a sort of corkscrew type killing vector. So just to show, because that's the case where you cannot, in any natural way, that's the generic case, and in that case you cannot in any natural way associate space to a slice. So I could take a slice and say I'm talking about, so a point of this m bar is this whole world line. I could slice it any way I like and say I'm talking about an orbit in that slice. but this whole construction is not forcing us to do that. That would be, to do that would be saying to each value of x1, x2, and x3, associate a particular t. That would be how you would get a slice, right? Once you've done that, then you can think of this space as living in that slice, but you can just as well take another slice or some other slice. And here we haven't taken any slice at all. We've just asked what's the succession of spatial coordinates that the orbit runs through, right? It's the actual orbit, the world line runs through. So the actual world line is doing something like this, whatever. And it's certainly, of course, not staying in any slice. So this distinction is subtle, but it's actually very important when it comes to things like Kaluza-Klein theory, and what people call brain worlds or something like that. So in all those theories, space-time is actually of a higher dimension than 4. In the simplest case, it's 5-dimensional. But in what are called Kaluza-Klein theories, in the narrow sense, a point of, so you have these, it's just like this, but this doesn't represent time anymore. It represents the 5th dimension, something going on in the 5th dimension. And these things actually close back on themselves. They're circles. And in that situation, if all you have is a 5-dimensional metric with a kind of symmetry like this, then a point of the 4-dimensional space-time is precisely a point of this kind of quotient space. A point of 4-dimensional represents a little circle in 5 dimensions. That's, on the other hand, you could say we live at a particular location in the 5th dimensional. There's some submanifold analogous to this slice you were talking about, some slice in the 5th dimensional sense, and that's where we live. That gives a physical reality to that slice. That's called a brane, B-R-A-N-E, like membrane without the mem in it. That's a very, very different theory than one in which we just represent a quotient. So in one of those, in the old Kaluza-Klein theories, you could say we represented a quotient of the 5-dimensional space-time. And in these brain world scenarios, you could say we represent a submanifold. We live on a submanifold of this 5-dimensional space-time. And they're actually very different. Although not everyone, people who studied Kaluza, before these brain world scenarios became popular, many people would write about Kaluza-Klein and they would get confused and they would think that it was a brain world scenario, which it's really not. But I used to say those were the people who just didn't understand the theory. But it turned out those who didn't understand the theory are now the majority, in the sense that it's more popular, probably. Well, I'm not sure. Partly more popular. Anyway, just one other thing I wanted to say, yeah, which is there would be a natural, in some situations, there would be a natural way to identify this quotient manifold with a slice, and that would be orthogonal. You know, if you could find a slice that was everywhere orthogonal to this killing vector, that would be a natural choice of slicing. That's what, then one says that the killing vector is hypersurface orthogonal. But, but you can't, for the reason that we saw in the problem set, that we saw in class also, that would be amount to being able to synchronize clocks along all of these world lines of the killing vector. Because orthogonality means simultaneity. And we saw you can't do that. And in general, you can't do that whenever there's some twist in the killing vector. So when you don't have when you can't choose this orthogonality condition, there's no simple natural. It's hard to say what's natural, but I think most people would agree there's no natural way to choose a slice. And in any case, we don't need to. Okay. So let's, with all those introduction, let's go and try and prove, let's just try and play around a little and derive the Fermat's principle for the case of light. So we're interested now in the case of the massless particle. Then in that special case, we know that S is just 1/2 dx squared over d lambda. And we know furthermore that at a solution, on shell, as people tend to say, at a solution, dx squared is equal to 0, right? It's going, we proved that. Or you can see it up there. Or you can see it here, sorry. Just by varying lambda, d lambda, you can see that it's 0. And anyway, we know. So something going at the speed of light, dx squared is 0. So now let's make a restriction. We'll consider only light-like world lines, only gamma such that dx squared equals 0. Only null, only ones whose tangent vector is null. So that's a standing restriction. I'll never consider any curves, any world lines that don't satisfy this in the following calculation. Now, because of that restriction, we can do the following calculation. Remember, because of that restriction, I should have said, that means S of gamma, no matter what gamma we consider, it's 0. Okay. So, because the integrand itself is 0. So if it's 0, then when we take its variation, it's also 0. And if we vary about a solution, then as we know, as we have seen many times now, the variation of the action is given by this condition. And if we write out what that is in this coordinate system, it's P naught variation of t plus pk variation of xk, right? Where, of course, k is always running from 1 to, it's always just a spatial coordinate. And this can be written. So let's now we're interested in a variational principle for this orbit. So let's do what you normally do in variational principles, is fix the endpoints of the orbit, right? So I'll just fix this to be 0. So that is, I'll just consider variations in which I don't vary the endpoints of the orbit. But that doesn't say that the time doesn't vary at the ends of the orbit. In fact, it must, right? So if I hold the endpoints fixed and vary the orbit and say that it's going always at the speed of light, then of course the elapsed time must change. So under that assumption, so this is just an assumption here, or how do I say, a restriction. Under that restriction, then we can write this equation. But now, remember, the crucial thing is that this, so I can write this as, using the fact that P0, which I've used a couple of times, P0, did I write it somewhere? P0 is equal to minus, remember what that means, it's equal to, in complete generality, it's equal to the zero basis vector contracted with P. But the zero basis vector in these coordinates is the killing vector, so it's CAPA. And that, of course, is the energy. That's the conserved quantity, except that with this particular signature, it's minus the conserved quantity, if you remember from special relativity. So it's P with the, in flat space, it's P with the contravariant index 0 that represents the energy. So this is minus the energy. So we can write this as minus E2 delta T2 plus E1 delta T1, right? And these go away because we fixed these spatial endpoints. But now remember, of course, the whole point of the killing vector is that the energy is conserved. This thing here is conserved. Since it's conserved, that means it's constant along the world line. I can just call it E, and I can take it out in front, and I'll get minus E times the variation of T2 minus the variation of T1. But that's the same thing, obviously, as minus e times the variation of the quantity t2 minus t1. So what have we got? We took an arbitrary world line, but then we limited it by the assumption that it's going at the speed of light, and then we also limited it by saying that we won't vary its spatial endpoints. And we found that under those limitations, the variation of the elapsed time is 0. So the conclusion is that variation, if we drop the e, the variation in t2 minus t1 equals 0. So if I write that in words, so this is Fermat's principle. If I write that now in words, what it's telling us is that t2 minus t1 is an extremum among all spatial paths, orbits as I've been calling them, that go at the speed of light from between fixed endpoints. That's Fermat's principle. Sometimes called the principle of least time, but it would be, as far as what we've proved, it would be more accurate to say it's a stationary time or an extremal time. It's a principle of extremal time. But in most cases, it'll quite often be the least time. Yeah.
Sorry, I was going to ask about the fact that that the coordinate time shows up here rather than some sort of proper time, and then I realized it's kind of a silly question for a massless particle.
No, it's not a silly time. It's not at all a silly question, because the time that we're talking about is not the time of the particle. It's the time.
Yeah.
It's the time, what you might call laboratory time or solar system time or something like that. And then, so that's the time measured by people who are stationary in the solar system, not this object which is moving through the solar system, but those who are not seeing the change, who are not seeing the gravitational field around them change with time. So it's not a silly question. In fact, it's a crucial question. They could have used their clock time, but the important thing to observe is that you're not to use the clock time. You have to use this killing time. So let me write that down. So t here is killing time. It's not clock time. Of course, if you're doing something like light going past the sun and you're sitting out at a great distance, there's almost no difference between killing time and clock time. But if you were to go near a black hole or something like that, then as we saw, there's a big difference between killing time and clock time. And in fact, if you remember the discussion that we did when we talked about the redshift and so on, if you want to see the metric look stationary in your coordinates, then you cannot use clock time. So it's a typical case that even when there's a killing vector and there's a coordinate system in which the metric does look stationary, it doesn't read off clock time. And that's because of the redshift, because the proper time runs, so to speak, with respect to that killing time at different rates in different locations. The shorter. Okay. So it's important that that be the time. So now, I'm not going to go through, again, actually working out what this is, but it's close. You can. I mean, we've seen things very similar when we discussed reference frames. So let me just write the formula. So this t, which I mean, I'll just call the difference now just t, the elapsed time. We can now work out what it is for a particle moving at the speed of light in a stationary field, and we get this formula. It's this I'll say what these are in a second. This is the spatial distance, the one that we talked about, the distance measured in the reference frame of these people moving at the killing vector, following these people whose world lines are the integral curves of the killing vector. And in other words, stationary observers, as you might call them. I don't know why I wrote it exactly like this. Anyway, let's leave it like that. So that's you can easily work out. It's very close to what we did before. You could work out this formula where I've introduced maybe a new notation. So this phi is the Newtonian potential. But if you remember, before we defined the Newtonian potential only in a linearized situation when you were close to flat space. Here there's no assumption that you're close to flat space, but there is an assumption that you have strict stationarity. There is a killing vector. So this e to the phi is just the natural generalization of what we had before. It's the square root of minus g00 in this frame, but if we think of it in a more geometric way, it's right. G00 is you go back to this connection between the time-like basis vector and the killing vector. The G00 is just the squared length of the killing vector. So what the redshift is really telling you is that when there is a killing vector, it's telling you that the rate of the local clocks is given by the norm of the killing vector. So this generalizes what we had before. Before we had the approximation that e to the phi is approximately equal to 1. Of course, this G00 would be e to the 2 phi. So let's work with that. So e to the 2 phi is approximately 1 plus 2 phi. We said when G00 was about 1 plus 2 phi minus G00, that this was called the Newtonian potential. So this is just we can use that name for it more generally without getting into trouble. And then the other thing is the dl squared. dl is the spatial line element, which we know and love. So that's this gj. That's this thing here. Which is subject of the homework. There was some delay in some of the homeworks getting in, so I just started grading them today, but should get them back on Tuesday. So that was the subject of one of the homework problems. And then then in the special case, where it is hypersurface orthogonal, or what's called static, where you can find slices that are orthogonal to all the killing vectors, which is a killing vector everywhere, and you use those for your calibration of time, then the G0k's go to 0. And in that special case, of course, it just reduces to the integral of dl over e to the phi. And dl squared is now, and dl squared itself is simpler too. It's just gjk dxj dxk. So that's a special case. So I could have used abstract indices here, but it wouldn't have been worth the effort because we'd have to introduce a different kind of abstract indices for the quotient manifold and for the space-time as a whole. And so once you're used to them, you should see that there's really nothing that really involves the coordinate system going on here. Anyway, so that's the special case, and this special case would be the one that would apply to orbits of light in the neighborhood of a Schwarzschild metric. So we could use that for Schwarzschild. A couple of remarks are when we actually come to Schwarzschild, it'll be just as easy to use conservation laws directly and not go back to the Fermat's principle, especially because I didn't show you Fermat's principle or the analog. I think it's called Maupertuis principle or something, but I never can get all the names straight. But I didn't even show it to you for the massive case. But from looking at this, you learn qualitatively, you can get a lot of intuition about what's going on. So the first thing I already said is that you see that the norm of the killing vector basically represents, that is the size of the killing vector, basically represents the gravitational, or its log basically represents the generalization of the Newtonian gravitational potential. Another thing to notice here, when this G0k is not 0, is that you see that the orbits won't be reversible, because if I run the orbit backwards, this dxk will change sign. Nothing here will change sign, because if here's the sun, and I have some orbit like this, whatever it is, doesn't look very much like an ellipse, but anyway, it was supposed to be an ellipse with a little bit of precession. But anyway, that this term involves only arc length along the orbit and the local value of the potential. So it's reversible, but this term is not reversible. This is what you get when you have a spinning star or a rotating star. And so you see that the orbits in that case, the retrograde, what are they called? Prograde and retrograde, the orbits that go in the direction that the star is spinning, and the ones that go the opposite to the direction that the star is spinning, will not be the same orbits. There's a kind of breaking of time reversal symmetry. That's one thing that's obvious from this formula. Another thing, well, I'll just say them in words. I won't bother to write this all down. Another thing that you see from this formula is that when you get near the sun, remember this phi gets smaller, so the Newtonian potential is becomes more negative or gets smaller when as you approach a massive body, and what it means is that the norm of the killing vector, because of this being negative, then becomes less. The killing vector becomes shorter, and that means that the local time slows down, which is reflected in this formula. So the time it takes to go a distance dl is not, in killing time, is not just dl, but it's rescaled and it gets longer. So that means if we use that notion of time as our time, the killing time, then we would say that light slows down as it approaches a massive object. So maybe I will write that. So we see from that first thing that light is retarded near the sun or any other thing that would be attractive, that have which it always will, because it's a positive mass. This is called sometimes the Shapiro's time delay, and it means that you can think of the neighborhood of the sun or the Schwarzschild metric as if it was a kind of refractive medium. And all the conclusions are the same, right? So if you have a refractive medium which is more, refractive index is higher, closer to the object, and more near 1, or far from the object, then you know what a wave packet will do. A wave packet will come like this, but since the inner part will be slowed, the wave will bend, and that's the bending of light by the sun. It yields the Newtonian value. What you would just, if you imagine that the photon, as we'll see, I think, if you imagine that the photon was just some particle, Newtonian particle going at the speed of light, then to a first approximation, the bending you would get would be exactly the one that comes from this term, because in fact this term involves nothing but the Newtonian potential, at least in this approximation here. But then the second thing to notice is that there's another correction, because this is not the flat metric. It's not just, I mean, the metric itself is not flat in the Schwarzschild case. The spatial components are not flat, but in fact this is, well, in Schwarzschild there's no distinction between. But if there was rotating, then there'd also be a further correction due to the, this thing that we call gamma is not exactly equal to jk in general. But in the Schwarzschild case it is. But in any case, distances are also distorted as you get close to the sun. And that actually slows it down even more. So it causes more bending. And, I wouldn't say, by it slows it down more, I mean, you end up taking more elapsed time along a given orbit than you would have had the purely spatial geometry been flat. In fact, that's the famous, if you read something about the history of relativity, that's the famous factor of 2. So each of these effects from the changed geometry and from the redshift turn out to have the same value, and so it looks like a factor of 2. But they're actually 2, from this point of view, completely different effects that just happen to be equal. But that's why that the relativistic bending of light by the sun is twice what the Newtonian one would have been.
When you say the Newtonian curve path of light, how do you deal with a massive particle in Newtonian mechanics?
Pretend it's massive. Just think, the point is that the mass drops out, right? That's the equivalence principle. Mm-hmm. So the orbit of any particle in the gravitational field depends only on its velocity.
Right.
So yeah.
Okay.
So that's what I mean.
Right.
And then the final comment is that maybe I'll skip that. I won't say any detail about that comment. But the way I've described it, this Fermat's principle depends on the existence of a time-like killing vector. There's actually a version of it that's independent of that, that works in general, that Joseph Samuel proved. If you're interested, you could look it up. The next thing I want to do is apply some of the things we've just learned about conservation laws and killing vectors to thermal equilibrium in a stationary gravitational field. So, for example, thermal equilibrium in a, I don't know, what's a good example? Some sort of accretion disk around, well, that's not very much equilibrium globally, but let's say just some sort of imagine some sort of gas living around a star or a black hole, which is in temporary equilibrium, thermal equilibrium. So how would the temperature vary from point to point? That's what we'll see that there's a redshift. It's basically just the redshift again. The temperature will undergo a same redshift factor that a falling infalling photon does. Yeah, there's a question.
I'm just confused as to why the orbits, in the sense of the quotient manifold, are sort of what we need to be considering when we go out and operationally measure light bending by the sun.
Well, what do you measure when you measure light? I don't say you need to be considered. This is just a clean way of discussing what the orbit is. But isn't that basically... why is that not what we're doing? So the measure bending of the light by the sun, we're talking about... it's true that in that case, there in the case of Schwarzschild anyway, which is the one we're actually doing to a good approximation, there is a unique, unique orthogonal slicing. I mean, it's possible. So you could refer it to that, but you don't need to. And we're just sitting here on our reference frame, and maybe it could be a rapidly rotating star. So we're not timing the passage of the light by the sun. We're just saying, what you actually do, say in an eclipse, is you're comparing two trajectories, one of which is, you look at the same star or something like that, and you compare the angle that you see it at when the sun is there and when the sun is not there. So why do you say it's not? Are you trying to say that that's not well represented by this quotient manifold?
So this gamma bar map that you define, which goes from the real numbers to R3, we could have chosen, there are more than one coordinate system for which the time coordinate corresponds to the killing trajectory.
Mm-hmm.
Like you could use arbitrariness in how you choose your spatial coordinates. So wouldn't that change what gamma bar is?
So the arbitrariness in how you choose the spatial coordinate. So remember, a spatial coordinate is just a label attached to each one of these killing vector curves. So it's true that there's a sort of initial arbitrariness. You can choose them any way you like. But once you choose them, then they're completely determined. Once you choose them at some early time, let's say, then they're completely determined forever after. And the other ambiguity is how you initialize the clocks, let's call them, although they're not physical clocks. The clocks that tick off killing time, how you initialize them along these world lines. That's the only freedom that you have left.
So wouldn't the shape of your orbit?
Yes, of course it would. Look, in the coordinates different. So that would be, but that's something like saying, and it's also true that talking about the angle by which it bends doesn't have meaning unless it asymptotes to a straight line with respect to the metric near infinity. But it does. So in this case, the metric near infinity is flat. So we know what we mean by the angle. But if that hadn't been the case, that in itself wouldn't be a well-defined notion. But there'd still be this geometry of this. There'd still be the spatial geometry, and one could talk about the shape of the orbit with respect to that geometry. And then changing from one coordinate system to another would be no different from like changing from rectangular to spherical coordinates. You don't change the shape. You don't change the fact that an orbit is elliptical by representing it in spherical coordinates rather than Cartesian coordinates. There's an intrinsic geometry there with respect to which you can talk about the shapes, distances, and so on. And that's the one we computed when we discussed. That's that gamma. Its components are these gamma JKs. Remember, I didn't define them here again, but I forget actually what they were. But they were something, maybe people who did the homework, something like G0 up to a sign. There's something like this. I actually don't remember about the sign.
I think it was...
Which way? Minus?
Yeah.
Okay.
There's a question later where we basically had to use elementary row operations
to relate the determinant. Right. Okay, let me try and get through this. Is that okay? Yeah. Think about it a little bit. So let me try and get through a bit of this redshift now. So we'll consider a gas. So again, we'll consider a stationary field like the sun, or some maybe rotating star, which the sun is, but it's not going very fast. And then we have some gas, except some big box or something like that, and we have a gas around it. That's not an uncommon situation. And we imagine, I'm not going to have the sun shining, of course, that'll mess everything up. So we'll have a dark sun, something like that. And so that everything can come into thermal equilibrium, and this will have reflecting walls and so on, and adiabatic walls and so on. So imagine thermal, you might even put a heater out here to hold it at a fixed temperature, because we want to consider the gas at a fixed temperature. Now the first, I have to remind you some things, but first notice, or we'll assume if you like, that collisions conserve form momentum, PA. This is supposed to be a capital P. So this means that is to say the sum of all the individual momenta. So if a collision takes place, all these particles come in. We idealize it as being at a point. Other particles come, let's say it's an elastic collision, they bounce out. And then the same set of particles bounce out. Then the same is, of course, before and after. This, if we add up the form momentum, we get the initial and final, we get the same result. That's what I mean by saying that the collisions conserve form momentum. Therefore, a fortiori, in other words, it's obvious if they conserve the whole form momentum. Now, this vector, of course, has no meaning globally. That's an important problem in talking about conserved quantities in gravity. But I just mean it locally. It's at some particular point here, I'll call Q, where the collision took place. So this is meant to be in the tangent space to the manifold at Q. There it does have meaning, and you can talk about conservation law. Therefore, the collision also conserves PA CA, where CA is anything, but let's take it to be the killing vector. But now if we take C to be the killing vector, then of course not only does this total form momentum dotted into CA, let's call it the energy, not only does the total energy stay the same before and after the collision, but it stays the same in between collisions too. Because in between collisions, the particles are just moving around along geodesics and appropriate to their mass. And we saw that for those, along the individual geodesics, that the individual PA.CA stays constant. So the result is that the total energy, which is equal to minus the sum over all the particles of CA/PA, is constant. It never changes during all this process. I'm idealizing the gas as just the particles as not interacting except at collisions. Furthermore, I called this energy, is it really the energy? Well, yes, we've already seen that. So we're using this, if we use this notion of energy, if we use this kind of a coordinate system near infinity where everything is flat, so out here is infinity, or let's say someplace that's about flat, so that we can have a global notion of energy. If we have that global notion of energy, then, as we saw, P0 is just the energy per particle, and so that if we add them all up, we'll get total energy. So to the extent that total energy has a clear meaning outside of just this definition, we could say that this represents the energy, and so it's a natural generalization of the energy. It's also true for a photon. Remember, I'll just remind you something that I could have said before. For a photon, if we introduce a reference frame, then you know that the photon's form momentum is represented with the contravariant index in this signature, represented by the energy and the spatial momentum vector, where in the case of a photon, this E is h by omega, and of course, since it's going at the speed of light, they're equal in magnitude, so it's just in that reference frame, its form momentum is just some constant times a vector 1 v, where v is the spatial velocity vector. So again, it's true that the zeroth component of P is equal to the energy, which is H. I'm just reminding you things from special relativity. Now, the crucial thing, the crucial thing is what defines thermal equilibrium. So in thermal equilibrium, what defines it? Who remembers from thermodynamics? So we're talking thermal equilibrium at temperature T, which usually using the usual notation I'll call beta inverse, and I'll set K, which is Boltzmann's constant here, equal to 1, as people usually do also. So there's no K in this relation. So this is Boltzmann. So remember what is thermal equilibrium? If you have a system completely isolated, then it'll tend to, what do I want to say? If it's completely isolated, then it will evolve in such a way that the entropy is not increasing. However, if it's in contact with a thermal reservoir, which is one way of putting it at thermal equilibrium, then it's not the entropy will necessarily increase. It's isolated, however, energy will be conserved. However, if it's in contact with a thermal reservoir, energy will not be conserved, but the total entropy of the system plus reservoir will still increase with time. And it's maximized when the entropy of the subsystem satisfies this, right? So this is. I thought you might say that in thermal equilibrium you minimize the free energy. That's what defines the thermal equilibrium. This is essentially the free energy with it rearranged slightly. So it's the energy. It's the entropy minus beta times E. Basically, what it is, it's the total entropy of the subsystem plus the thermal reservoir that's maximized. So if we find some configuration so this is now just the energy of the system that we're interested in, this gas around the star, and this is the entropy of that system. This thing is maximized in thermal equilibrium, and conversely, thermal equilibrium is that situation which maximizes this expression. And from this we can derive, so you can say we calibrate the energy at infinity, if there is infinity. I'll put quotes. If there's not infinity, then you just have to find some fiducial location at which you would measure the energy, the temperature there, temperature and energy at that place. Okay. So now we're almost finished, but we have to do one more thing. So we have to imagine that this gas is approximately separable. In other words, if you look in a local region, you just see, if you like, by the equivalence principle, you just see some little bit of gas there. It's also in thermal equilibrium. So we're assuming there are no really long-range interactions in the gas that would prevent us from just thinking of it as an extensive kind of system. In other words, if we understand all the little local portions of the gas, then we understand the gas globally. So under that assumption, there has to be local equilibrium of the gas too. And there's one other thing that I had to stress that I didn't, which is crucial. And if you like, it's an assumption of this derivation, which is that the entropy is invariant. So the entropy is just a scalar. You know that we know that the energy of something may depend on the frame in which it's observed, for example, but the entropy never will. So it's basically because entropy is just counting states, just some log of some number of states. And it's a deep fact that the state counting is an invariant thing. So I'm thinking here of special relativity, but we'll assume also that it has some sort of invariant meaning in general relativity. So you just count the number of states locally, and then assuming that the entropy is extensive, so the entropies of all the little bits just add up to give the total entropy. If a lot of entropy was in things like long-range entanglement, which is quantum and we're ignoring anyway, but then forget it, this is a wrong assumption. But as long as we can treat of this kind of gas that we're thinking of, which is a very common case, then we can treat as S as invariant. And furthermore, it's defined locally. So now let's just look at this. This is maximized. Oops. Oh, no one caught this, but actually, oh, because I didn't write it wrong. I didn't yet make the mistake, which I thought I had. So if you can forecast, maybe you can predict the mistake I was about to make. So I want to rewrite this expression, S minus beta E, in terms of the killing vector. So remember, E was minus C dot P, so, and then beta is beta, some parameter, which we're identifying as a global temperature. So this has to be maximized. But it also has to be, under our assumptions, maximized locally as well as globally. If it's maximized globally, it certainly has to be maximized locally. If it's maximized locally, and if we think about what that means, this is equal to sorry, what have I done here? I want to rewrite this. I want to multiply and divide by the norm of the killing vector. Okay, so I want to split it up like this. This I'll call beta local, because what does this represent? This is now the normalized killing vector, so it could be the forward velocity of some local observer at rest in the gas. Let's call it UA, because it's now normalized, right? And so this is, and then this UA dot PA is then this is the total local form momentum. So this is just the local energy up to a sign, and so. No, I got this wrong here. So this little thing here is UA, and then the whole product of U dot P, that's minus E locally measured. Local now means measured by an observer using a normal, correct clock and so on, aligned with the killing vector. So this looks, so locally, if I write the whole equation locally, put local on everything, I'm just taking into account this portion of the gas, then again, this thing is maximized. That's telling us that the thing that multiplies the local energy is the local temperature, or the local inverse temperature. And we see that it's beta times C. So beta local is beta times C. So because temperature is the inverse, that means that the local temperature is the global temperature. I'll call it T infinity, right? Well, I'll just leave it as T over C. That's the key thing. This is as measured. When I say local, that means in the frame of the UA, where UA, which is equal to C over C, the normalized killing vector. This is what you might call the temperature redshift, or you might call it the temperature blue shift, because what it's telling you, in the sense the redshift occurs, I mean, the things closer to the star are redder, so this is saying, this is going the other way around. It's saying that the temperature closer to the star is higher. So it's like a blue shift. Well, I didn't forget. It's not clear those words are exactly unambiguous, but anyway. when you speak of, you can call this anyway, whatever you call it, red or blue shift, it's telling you that the temperature is higher as you descend in the gravitational field. Then I wanted to, using the relation between the norm and the Killing vector in G00, which you see over there somewhere, it's also, we can also write it like this. T local is equal to T infinity times the square root of the absolute value of G00 to the minus 1/2. It's just an equivalent statement in a coordinate sense. But this is the nicer way to write it, since it just involves the Killing vector itself. So I claim that this is almost, it's closely connected to and almost the same thing as what we found before, which is that a photon that descends in a gravitational field will gain energy and get blue shifted, and a photon that goes up will lose energy. And so if you think, I'll say, next time I'll say a little bit more about it, but if you think about it, it's sort of obvious that this had to happen, because if you might have thermal radiation in this, you will have thermal radiation as part of this gas, and if the photons are going to be in equilibrium, then they have to be cooler up higher than they are down lower, as measured locally in both cases. So there were some questions.
Yes, I was actually going to ask if that was the correct interpretation, basically.
Yes, that is the correct interpretation. Next question.
So in the case of Rindler, so if you go to in future infinity, you become null, which means that the norm of Kc goes to 0. So then,
yes.
So if you could then define some temperature, it would mean that for those observers, the temperature is blowing up.
Yes. Yeah. So from the Rindler point, as you know, from the Rindler point of view, I mean, of course, now you're probably thinking of the quantum field theory, but let's think of that. That's because I don't think it doesn't really affect much in the argument, as long as you don't have to worry about long-range entanglements. So as you know, from the point of view of this Rindler observer, it's locally as if it was thermal, the Minkowski vacuum. So the first statement is we looked at an equilibrium. This is all under the presumption that we're dealing with the equilibrium state. Okay. The equilibrium means it won't change in time and that it's stable. Small perturbations don't. Otherwise, it's not of any physical interest. It might, well, that's not true. It can be a physical interest if the growth time of the instability is slow enough. There's some indication that that's the world we're actually living in, so it better not. So there's some physical interest. But anyway, as long as the growth time of the instability, as long as there's no instability or its growth time is very, very long, then we can think of it as a physically relevant equilibrium. So, and furthermore, typically in thermodynamics, the equilibrium states are unique. So what is that state? Well, as we know, there is a candidate state which is which doesn't change with time, and therefore can qualify as thermal equilibrium for these observers. That's the Minkowski vacuum, because we know the Minkowski vacuum is invariant under boost, which is what this Killing vectors generates. Right? So this analysis ought to apply. It ought to tell us that as measured by the Rindler observer, that I mean, it's not strictly right because I didn't put it in a box and so on, but I could imagine designing a Rindler box, that would sort of, anyway, let's not worry about the detail there. So this is in fact telling us that the locally measured temperature will change. The closer to you get what you might call the horizon, the Rindler horizon, the higher the temperature. And in fact, it's the same thing, and it's the same thing as happens in the neighborhood of a black hole, as you know, because if you get close enough to the black hole, it tends to look just like Rindler. So they're all the same thing. Yeah. So it is true. Oh, what I want to say, as you know, and the way if you think in flat space, then it's what we call Unruh effect, and it's just a statement that the world, where is that picture of Rindler? Here it is. The observers who are closer to the horizon are accelerating more rapidly. They're basically these are basically circles analytically continued to complex time. So, if you like, these are just hyperbolas. And so, just as the radius, if you thought of it as a circle, its radius is its difference from its horizon. So it still has the sort of radius, or whatever you call this, of the hyperbola. That's the distance from the horizon. And this is just telling you that the temperature, and the Killing vector, if you thought of circles, the length of the Killing vector is proportional to the radius. So it's telling you that the temperature scales as 1 over the distance from the horizon, by which I mean this distance, actually. That's it. If we call that R, then the temperature is scaling like 1 over R. And that's indeed true.
But if you gave an observer, such an observer, a detector, then close future infinity, the detector wouldn't find itself in a thermal equilibrium with infinite temperature, would it?
Oh, no. Is that supposed to, I hope. So remember I said that if you were at infinity, yeah, that's a good question.
Okay.
So there's an arbitrary sort of calibration going on here. But if there is infinity, and if at infinity you use the local notion of energy, which means that you're stationary, it means that you're purely time-like Killing vector at infinity, then this would be true. So exactly. So in Rindler, that's not the case, because you're not. No matter how far you go out, you're not actually using. You're not. Well, as you go farther and farther out, so like you go way out here, well, you can hardly see that there's bending. So it's almost like the time-like Killing vector. But the normalization is wrong. Right? You have to use the normalization where this is where the norm of the Killing vector goes to 1 at a. Maybe I should write that here. So that's the way we normalize at infinity. So if there is infinity, then we normalize it so that c goes to 1 at infinity. But when you use the Rindler boost Killing vector, then it's getting bigger and bigger at infinity. Yeah. But what's always going to be right is the ratios, the relative redshift or blue shift between one place and another place. I think that makes sense what I'm saying. Yeah. If you look in detail at some of these discussions of the Rindler vacuum and whatever, then you'll see that actually the temperature that's used there is really an angle. It's dimensionless, and it has an arbitrary normalization in it. If you want it to be a real temperature and not just not a pure number, it has an arbitrary normalization in it. And you basically can just key it to anyone. You can say, I mean by T the temperature that this person sees, and then you'll get one set. Or you can say, I mean by T the temperature that this person sees, and so on. But you have to. You have to use that for your global T. Other questions? Okay. See you next week, I guess.